Today I'll be talking about how to get information about the Halo Galaxy connection with machine learning. My name is Raul Abramo from the Physics Institute of the University of São Paulo, and I'll be reporting about work which was done in our group together with Santi, who is going now for a postdoc at the Flatiron Institute in Berkeley, Natalia Rodrigues, who is a PhD student that's finishing this year, and also Antonio Monteiro Dorta from the Universidad Técnica Santa Maria in Chile. And my main motivation for doing this comes from a survey that we are conducting in a new survey called JPass. And part of the survey will be done in connection with the WEAVE survey. So WEAVE is an instrument in the William Herschel telescope in Spain, and it has one of its surveys is called WEAVE QSO, which will target high redshift quasars. So JPass is a narrowband optical survey, which is being conducted from a telescope in Spain. It has 2.5 meters. It's dedicated to the survey, and it's now taking images of the sky using 56 narrowband filters. Each filter has a width of about 100 angstroms, and we already have about 300 square degrees observed, and we are aiming at a speed of about 800 square degrees per year on this survey. The first public or early data release should be by the end of this year in 2004. Here's some pictures of the telescope. Here in the lower left, you can see a figure with the actual measured filter transmission curves of the narrowband filters. And here is an image of our focal plane, which has 14 CCDs. Each CCD has a filter, so it's kind of a quite complicated way of covering the sky. But with the proper tiling strategy, we can do it. This is described in the paper Bonoli et al. 2022. Now, JPass will have a huge number of sources, about 1 billion sources, about 5 times 10 to the 4 objects per square degree. Each object will have a low resolution spectrum or a pseudo spectrum, and we will reach signature noise of greater than 5 in basically all these filters for objects which have magnitudes in the R band lower than 23. So this is basically 2 magnitudes deeper than, for instance, SphereX. So this is a much deeper survey than SphereX, although we're going to cover an area which is a few thousand square degrees, so it's going to be smaller area. We have about 10 to the 4 galaxies per square degree that can be used, which have photosys better than 1%. And we also get, because of these pseudo spectra, the galaxy properties. In the figure here, you can see actual data overlaid with the spectra from Sloan for objects such an emission line galaxy, a luminous red galaxy, also here are quasars, right? And you can see that you can derive not only, you can determine the class of the object, whether it's a star, a galaxy, a quasar, and so on, but we can also derive the redshifts and also some other properties of the galaxies, right? So this data sample, this data set will be a superb way of doing a multi-tracer survey of the universe, especially below redshift 1. We will also have a large number of quasars. In fact, JPass is an absolutely superb object with which we can measure quasars and in general emission lines. This little plot, this little movie here shows how, for instance, an emission line galaxy at different redshifts would appear in our filter set, right? So for quasars which have broad emission lines, this is even more so. We can see very clearly these broad emission lines here of the quasars, which will very uniquely determine their type. However, we have, very many objects and we have very few quasars. So quasars are about 0.1% of our sources, and the high redshift quasars are even less. We have about 75 quasars per square degree at redshifts greater than 2.2. And these are extremely high value targets because they reach way deeper into the universe. Our quasars, the quasars detected by JPass, will be followed up by the WEAVE survey to study the Lyman alpha forest with those quasars. And the fact that we have a denser sample compared with DESI will be key in this strategy here. So we'll have a smaller area compared to DESI, but we'll have more objects. However, to find those objects, these are really needles in the haystack. We need to find in a billion objects, which you need to find in a few 100,000 quasars. And there's no other way around to do this other than machine learning. And however, we cannot use machine learning unless we have a training set, which in this case doesn't exist. So we have to create our own training set. So we forward simulated the JPass data all the way from luminosity functions and SDSS spectra down to JPass fluxes and magnitudes using real uncertainties that were collected in the 1 degree mini JPass survey. This is described in Queiroz et al. 2022 paper. And then on the basis of that, we then use convolutional neural networks and as well as other machine learning methods to find the quasars and especially the high redshift quasars. This is described in the paper by Natalia Rodrigues, which is over here. Natalia Rodrigues et al. 2023, as well as a few other papers from our group. So now this is the motivation, and now for the work that I'm going to report today here. How to go from halos to galaxies using machine learning. So the idea here is that we want to study large scale structure, and a very important piece of that puzzle comes from the numerical simulations, which allow us to go from the larger scales to smaller scales to really simulate halos, and eventually even with hydro simulations to simulate galaxies. However, n-body simulations are expensive enough. Hydro simulations are much more expensive, but in some sense we need to predict how the galaxies form in halos and how they connect to the halos into the large-scale environment, so that we can understand how to connect our observations to our theory. So our tracers are really they are detected on the basis of objects that emit light. So baryonic physics is key there. However, this precise relationship between the halos and the galaxies can be very complicated, and we've had for many years methods to do that connection, like semi-analytical models or subhalo abundance matching models. We are now looking at a different way of looking at this, which is to use machine learning to try to predict with high accuracy how galaxies form inside halos, in particular how central galaxies, for most of my talk here, how they form inside halos, how they depend on the halo properties and in the large-scale environment where they are found. To do this, we use the IllustrisTNG hydro simulation. There are many papers discussing how this the simulation and the galaxy populations that are predicted in those simulations here. These papers down below. And this is work that was done with Nathalie de Santi, which is over here, Natalia Rodrigues, Antonio Monteiro Dortas, as well as Beatucci and Celeste Artale. So the earliest attempt that we did for this was to just try a regular regression to treat the way in which we go from halos to galaxies as a regression problem. So basically, we use the halo properties and we try to obtain through regression the galaxy properties like stellar mass, star formation rate, radius of the galaxy, and color. So basically the inputs are the halo mass, halo concentration, spin, age, and the local environment, delta 3. So that's the, let's say, variance of the, that's the density over a 3 megaparsec radius. So that's the input. The output are the galaxy properties. And then we have to train our models in this way. However, one common problem that we find, in no matter how you approach this kind of a problem here, is that we have some small but very important populations which are underrepresented in your data set. So for instance, red massive galaxies, there are just a few compared with the much larger sample of blue galaxies, star forming galaxies, and so on. So we need to balance that so that the machine learning knows to represent well the most important populations. There's a technique for doing this. This is called, so we have to use data augmentation. There's a technique which is specially made for these imbalance regression problems. It's called SMOG-N, and here is a reference for this technique here. And we use this. So in this plot here, what you can see is how we predicted the galaxy properties from the halo properties at redshift 0. So that's the paper from Nathalie de Santi et al. 2022. On the left plot here, the left column are the initial predictions of the regression without any data augmentation here. So the black lines are the true populations, and the colored points are the predictions from this regression. Now you can see that in this case here, we're talking about the halo mass and the stellar mass relation, or the halo mass and the galaxy radius here. When we use the SMOG-N technique, this gets a little bit better. You represent better the populations which are at the outskirts. So basically, if you don't use data augmentation, you over predict the mode of the distributions, but with data augmentation, you can mitigate that. And that's even more true when you go to more complicated parameters, galaxy properties like the star formation rate or the color. It gets, so the data augmentation makes a really big role in there. However, there are some problems here that we pointed out in that paper that we need to solve. First, still, even with data augmentation, the mode of the distributions is still overrepresented. So the tails are underpredicted, the mode is overpredicted. Moreover, each galaxy property was trained independently from the others. So you're making a regression problem which is not a joint regression. It's like each property you predict independently. And finally, this method here is basically fully deterministic. So given a set of halo properties, there's only one final answer for the galaxy properties. And this cannot be true, of course, because there's a degree of stochasticity involved, and we need to know what that degree, what that stochasticity is. Now, we know that galaxy properties are in fact correlated and to some level stochastic. So what we did then in this following paper by Natalia, which is over here, Natalia Rodrigues et al. 2023, is that we predicted the joint distributions of central galaxy properties. So what we did in this case was that we split the n-dimensional parameter space into discrete classes. We did this usually in 2 dimensions. So we picked 2 galaxy properties, in this case here, for instance, color on the horizontal axis and star formation rate on the vertical axis. And then we divided that into cells here. So basically each dimension, you make a grid, and then you look at the cells here, and then you apply a neural network classifier, which assigns a score to each class. That means to each point in this parameter space here. So this improves dramatically the accuracy of the predictions here. So on the left here, you see the true distribution here for color and for set formation rate. You can see on the middle plot what we were getting with predicting each galaxy property individually, that the individual distributions were being properly predicted. However, the joint distribution was terrible. And this was, of course, solved by having these classes here, and then we can predict basically perfectly this very complicated relation between color and star formation rate. Basically here are in the bottom right are the red galaxies, red passive. On the top left are the blue galaxies, and in the middle here we have some kind of a green valley galaxies here, right? This population which is neither blue nor red. We can also ask in this context, what are the most important halo properties that correlate with the star properties, right? So, for instance, for stellar mass here on this inset here, we see that the halo mass is the most important parameter, followed by concentration, spin, age, and these are here now basically very unimportant compared with mass. Right? So this is basically, they are 100 times less important than mass and significantly less important than concentration. That's for the stellar mass. And we know this for a fact because stellar mass is highly correlating, it has a high correlation with halo mass, especially, as you recall, we're doing this for central galaxies. So this correlation is well known. Now, if you go to star formation rate, for instance, in this case here, we are always using specific star formation rate. So this star formation rate divided by the stellar mass of the object. Then we find that still mass is very important. Now, concentration is not so important, or actually, depending on the method, it may be less or more important, but actually now age is very important here, the age of the halo. So the last major merger, when it happened, this is very determinant for this, for the importance, for how you determine the star formation rate of a galaxy. But also spin here, surprisingly, is important. So how fast the galaxy is rotating. In all models, this becomes, almost of the same order as the age in importance. Finally, the local environment is again, seems to be relatively unimportant. Of course, there is a huge number of other parameters that we could have used here, and we have actually tried. However, we always see this hierarchy of properties here. The four most important properties are mass, concentration, spin, age, and sometimes the local density makes a role. And most other halo properties we found to be unimportant or to have vanishingly or undetectably small influence. Of course, all of these contribute to some level to what happens with the setup, with the properties of the galaxies. However, it's like all of these other properties are actuating in a way such that they are pushing and pulling the properties this way or that way, in such a way that the properties of galaxies, they are random because of this infinite number of smaller importance features. However, it's uncontrollable, and of course you can ask whether or not a simulation will capture all of this. So there's a degree of stochasticity. It's like these properties are following kind of a slide of a bit of a random walk, and it would be folly to try to frame this problem into a fully deterministic sense. There is a degree of stochasticity that's there, and we ought to try to capture this stochasticity. Now, one of the interesting things we can do when we are able to predict the galaxy properties in this way is that we can divide our galaxy populations into different populations. And here on the bottom right, you can see what happens when we use stellar mass and color to divide the entire population into 7 populations. So population alpha equals to 1 is the, let's say, red galaxies, but less massive. Alpha is equal to 2 is the red, very massive galaxies. Alpha is equal to 7 is the blue, more massive galaxies. Alpha equals to 6 is the blue, less massive galaxies. And then we also used 3 populations of, let's say, green galaxies, if you want. And then we can compute the power spectrum, the clustering of these objects here, and we can compare with how well we are predicting the clustering of those objects. For each, so the first line of plots here are the power spectra for the populations alpha is equal to 1, 2, 3, and 4. And basically in purple, you can see our prediction, and in the orange dotted and light orange dot dash lines, you can see the univariate predictions, which are very bad. So this shows clearly that, these plots here also for the other populations, that predicting galaxy properties individually without taking care of their correlations with the other properties leads to bad predictions for our tracers. Now, basically we are at the limit of cosmic variance here for the accuracy with which we can predict the clustering of these populations with our method. However, it's interesting that also you can imagine that the stochasticity of galaxy properties also means that when we compute the power spectra of those populations, there will be a kind of a variance associated with that stochasticity. And this is what we quantified also in our paper, Rodrigues et al. 2023. Now, the second row here shows you the relative contribution of the galaxy property stochasticity to the Paul spectrum. So in some cases here, you can see that the contribution of that stochasticity is sometimes of order about 10%. And that's even on small scales, right? So it's something that's going to be there no matter how large your galaxy survey is. So stochasticity of the properties that define our tracers is something that has to be properly accounted. And when we choose the tracer populations that we're going to use for our cosmological surveys, we have to be aware of that stochasticity. Now, there's still some things which were not optimal in the way that we were doing things. For one thing, we were using grids in 2 dimensions in the parameter space of the galaxy properties. And this, of course, we wanted to do this for all the dimensions we want and not just for 2. However, tiling or gridding are highly inefficient methods when you use higher dimensions. So with many galaxy properties, this becomes unfeasible. Moreover, some parts of the distributions were not still perfect. They were being not well represented, even with the classification that we had. Besides, some of the metrics that we used to capture how faithful our predictions were still not perfect. So we worked further, and this is the paper that we are preparing right now, together with Natalia, Nathalie, myself, and Antonio Monteiro d'Horta, and should appear in just a few weeks. We tried a couple of different approaches here. One of them was that instead of doing tiling and gridding, we defined classes in terms of Voronoi-based algorithm for creating these classes. So basically, it's a hierarchical Voronoi algorithm that defines classes in any number of dimensions. The advantage is that these classes have a certain fixed number of instances, which is what you need in order to train any of these neural networks. So that's one way of solving and going to higher dimensions. Second, we also tried a very simple approach where we said that for each object, the target, so in the galaxy parameter space, the probability should be Gaussian, right? So basically the neural network should basically predict the expectation value, the mode, and the variance of each of these targets, each instance. So that's a very simple model, basically, for treating the problem in a statistical, in a stochastic sense. And finally, we use also the technique called normalizing flows, which is a way of mapping a very complicated distribution into a much simpler one by a series of invertible maps. And this is shown kind of in this little movie here for some comic relief here. But in practice, what you have is some high dimensional, in our case, 5-dimensional properties of halos and 5-dimensional properties of galaxies. And we use normalizing flows as a way to obtain distributions that we can then model much better, instead of having something which is, multimodal, that has complicated correlations between different dimensions there. Okay, so some results here. Typically, the color stellar mass space is one which is kind of hard to reproduce here. And this is what we are able to do for the normalizing flows. So each plot here is one machine learning technique compared with the actual data. The data here is in gray, and the machine learning technique is some color. In this case here on the left, in red, is the normalizing flows prediction for where you would end up in the stellar mass color space for each one of the central galaxies in our Illustris Halos. In the middle here, we have the neural network using the high-val classification scheme, the hierarchical Voronoi allocation system for creating these classes, and they are very similar. But you can see here that the neural network classification fails a little bit when there is a big gradient in the distribution here. So when the mode gets cut off, And in this case, the cutoff is totally arbitrary. It's just a matter of resolution of our simulation. However, the machine learning doesn't know this and but in any case, it doesn't reproduce this well enough in the case of the classification scheme. Whereas the Gaussian approach, it just fails really badly. I mean, it doesn't capture the entire distribution. It just predicts things which are out of sample. It's just not working well at all, but it serves the purpose of making a comparison. Ultimately, this was an exercise in showing how normalizing flows, not unexpectedly, is a superb method for trying to predict properties such as galaxy properties on the basis of halo properties in a way that captures the whole probability distribution functions associated with those objects. Here is another way of looking at this. This is again the stellar mass color space here. The truth is in the gray contours, and each method here is now overlaid, so you can see how normalizing flows reproduce extremely well the actual distribution, followed by NN class, which is good but not perfect, followed by the Gaussian approximation, which is just terrible, right? And here are three metrics that we are using to monitor how well these techniques are working. First one is the Wasserstein or Earth movers distance. So this is basically a metric for how different the distributions are. So you compare the true distribution here with either one of the other ones here, and then you measure the distance there in terms of this Earth movers distance. And in this case, the closer you are to zero, the better you are. And you can see that basically for stellar mass, color, star formation rate, and radius, normalizing flows and NN class are doing very well, whereas the Gaussian approximation fails miserably. For the KS test, again, you see that normalizing flows is typically the best method, and the Gaussian approximation is worse. However, the Pearson correlation coefficient here, which now the closer you are to 1, the better it is, you can see that normalizing flows is significantly better, especially for star formation rate here, which is critical for predicting galaxy properties, for dividing traces, and so on. So the winner is for sure normalizing flows, and this is a way of proving that you can do extremely well, and you can have some you can actually predict to some level these properties. However, we do not believe you can do much better in some of these parameters here because of stochasticity. And I'll talk a little bit about this in just a few moments here. Now, here are some results here for the 2D distributions. I already showed stellar mass and color, but here also stellar mass and star formation rate, stellar mass versus radius, and color versus star formation rate for all of these here. One interesting metric also to measure these by is the so-called coverage. So you look at the entire distribution in the 4-parameter space of stellar mass, color, star formation rate, and radius, and you ask if you are over or under predicting objects there. So this test is telling you that the Gaussian approximation over predicts the lower likelihoods and under predicts the higher likelihoods, whereas the NN class does the opposite. It just under predicts the low likelihood and over predicts the high likelihoods. And finally, normalizing flows is really following this line perfectly. The better you are along this dashed black line, the better you are. So again, normalizing flows is the best. Now, I already said that you cannot do perfectly here in some of these tests because of stochasticity. So what is the degree of stochasticity? Here is a very interesting plot. I think it's one of the most interesting plots that we can build here, which is when we ask the following questions. Let's not ask what are the distributions for the entire population of halos and galaxies that we have here, but only for a subset of those halos. So for instance, let's look on the left here at the very high mass halos. So halos with masses greater than 10 to the 12 solar masses. And then you can ask, what is the distribution of the galaxy properties? So this is again stellar mass and color. What is the distribution of these properties for those heaviest halos. And then you find that this is the distribution in stellar mass and color. So as you would expect, the heavier halos also have red galaxies and massive galaxies. The scatter is more on the mass than in the color because they are really basically passive. They are as red as they can be. But the mass range still varies by basically 2 orders of magnitude here. And that's what you have. You can have central galaxies which have 10 to the 10.5 to 10 to the 12.5 solar masses there. Now, you can also ask the same question for less, let's say, less well-behaved galaxies. So if you have an intermediate mass halo, and then you ask, what are the properties of galaxies in these intermediate mass halos, you will find that now the opposite happens. The mass range is actually a bit more limited, although yes, we chose a very limited mass range here. So the mass here is really, the mass range in stellar mass is much wider than the mass range in halo mass. However, the most important feature here is that the distribution of colors of these objects here, they can go all the way from red to very blue, and a huge scatter there. Now, if we keep doing this and we go all the way to the lowest mass halos where you would think that they are populated by blue, less massive galaxies, you still find that there's a huge scatter. In fact, in color, it's absolutely huge scatter. Some of these could be even classified as red. Some of these are blue. But anyway, so this is the scatter that we find. So it has to be noted that there is nothing we can do to eliminate this stochasticity. It is an inherent feature of these galaxies. Of course, if you make a simulation with exactly the same initial conditions, you would end up with the same galaxy there, but that's not the point. That just the point is that you have a huge number of features that influence how galaxies form, how their star formation history evolves, and this cannot possibly be contained in any reasonable number of halo properties or even environmental properties that can be fed into any kind of a machine learning or semi-analytical model that can eliminate this stochasticity. So understanding this stochasticity is key for when we try to select traces for large-scale structure. Knowing if these traces are going to be populating the same types of halos and the same environments is key, and it's related to this stochasticity here. Just so that you understand better the level of these predictions here for the intermediate mass halos, this is how well you're predicting them with Gaussian approximation, with the classification scheme, and with normalizing flows. And again, normalizing flows is significantly better. Also, for this specific population of halos here, the coverage test performs very well for normalizing flows. So this is as far as we know, the state of the art for this for the understanding of the halo-galaxy connection, at least in the context of hydro simulations. Now, we've been talking here about how to predict galaxy properties on the basis of halo properties, but we could equally well turn this whole thing around and try to predict the halo properties from the galaxy properties. And it turns out that you can do it. This is preliminary. We are working on this, but basically there is also some degree to which you can associate the halo properties with the galaxy. So that gives you some hope of informing how we can derive halo properties on the basis of the galaxy population that occupy those halos. And again, this is only using central galaxies, so this is of course a limited set of information. But these plots show that you can reproduce the halo masses, the concentrations, the ages, and the local environments of those halos based on the galaxy properties. Of course, the plot on the right here, they tell you the uncertainties on those properties, but in any case, there is information there, and you can turn this back to go from the galaxies to the halos, and that's an interesting exercise that we are just starting to explore. Now, changing entirely the subject, the last 10 minutes that I have, I'll be talking a little bit here about how to get cosmology directly from galaxy groups and clusters. This is work that was done primarily by Nathalie de Santi with Paco Velasquez Navarro and the CAMELS team. So just reporting on work that was done in that context here. This work started, so the first part of the work here is more theoretical, but I'll talk a little bit in a second about how you can connect this to observations. So the idea here is that to some extent, the hydro simulations are reproducing some of the physics that goes into the distribution of baryonic matter in the universe. So if you look at gas, if you look at X-ray emissions, if you look at the free electrons, if you look at the different phases of the gas in the universe, these can be, in some coarse-grained sense, predicted by these hydro simulations, right? So the idea here is that we can then use those hydro simulations, and we can use a suite, so that many boxes with these hydro simulations, to try to train a machine learning algorithm to find the patterns and to reproduce these mechanisms that go into the formation of the galaxies there in these environments. So in this paper, Nathalie de Santi et al. 2023, it was shown that you can actually, just on the basis of galaxies and their immediate environment, so that means scales which are typically less than about 3 megaparsecs, that it was possible to infer the matter density of the universe. By the way, there's an interesting paper here which goes some way into explaining how it is that you can get that information back. So this was achieved in that paper by through the use of graph neural networks, and there's here some a link if you're interested in this. So basically, these are instead of having lists or points, this type of data set is a graph. So you have the nodes and you have the edges here, and you have also global properties of this graph here. So basically, what you see on the right here is a representation in terms of the graphs of one of the IllustrisTNG 25 boxes. So these are boxes of 25 h-1 megaparsec on a side. And each point here that you see is a graph. Also, you have some, or a galaxy and some linked galaxies here. So, so Nathalie, she used galaxies which are heavier than 1.3 times 10 to the 8. That's for resolution purposes, and a linking length of 1.25 inverse megaparsecs. So typically, the size of the systems that she was using had a few megaparsecs at most. So the properties of the graphs that she used initially were, first, the global features of the graph, so how many objects it has, something like this, maybe the total mass or some global feature, right? However, the most important thing was the positions and velocities of the individual galaxies. Also, the distances between the pairs, between each pair of objects in this. So this is what characterized the graphs that were used for this paper here. So Nathalie then trained the graph neural networks in one set of simulations, Illustris for instance, and tested this, the result of her graph neural network in another set. That's in order to see if the method was not just over predicting for the same simulation. So you can learn from a simulation, but is it able to generalize to another simulation and ultimately generalize to actual data? So the result is that the models are robust. So you can train in this plot here in the lower left, you can train in Astrid, for instance, in a test in Astrid. Of course, the result will be good, but you can then now train in Astrid and test on Illustris, and still your result, your prediction for omega matter is for each one of those boxes, for each one of these, the boxes with the same parameters, it still gives you a prediction which is good to about 10%. Also with another suite simulations called Magneticum. So basically, some parameters were not being predicted well, like sigma 8, although there is some progress in that sense from the CAMELS team, and but I won't be talking about this. But in this case, it was possible to recover omega matter with about a 10% uncertainty, which is really amazing, right? Now, of course, this is using the positions and velocities in 3 dimensions for all of these galaxies in the simulations. Of course, we don't have that information here, right? If you are observing things from Earth, we at most have 2 spatial positions and 1 velocity. So let's say angular position and redshift. So this is unrealistic. We have to do something which is more realistic. So in this other paper by Nathalie, 2023, we show that these results are actually robust to these real life features. So basically, now the inputs in your graph neural networks, they only have X, Y, and VZ. So that stands for angular position and redshift. And then we trained on the basis of only that information. So information about the Z position, Vx and Vy was completely eliminated. And then we retrained. We also used many other tests like errors in redshifts, masks, color cuts, etc. And still we found that basically all the time we could predict omega matter now, but now with an uncertainty which was a little bit larger, about 15%. Nevertheless, this is a proof of concept for the fact that there is cosmological information on small scales. You can recover them. Exactly what the machine learning is doing, it's hard to interpret, it's hard to tell. It's predicting, but we don't know exactly why. We have some let's say some guesses about this. It might be that the machine learning is kind of learning how to reproduce the Poisson equation and through that invert it to get omega matter, but it's very uncertain. We still are not sure about what is the internal mechanism that is being used to make these predictions about omega matter. Nevertheless, the message is clear. There is cosmological information, even in the small scale, highly nonlinear regime. Now, just a few words about what's next for us here, at least in that respect. Well, first of all, we have to go beyond central galaxies. We have to include satellites. We have to include all galaxies that we can observe reliably within the simulations. So going to the subhalos and the objects inside the subhalos. We also want to test for the predictions of the galaxy properties on the basis of halos, if they are robust, these predictions. So we have to see if training in one simulation and testing in another, if we still get the accurate predictions that we have, if the stochasticity is the same and so on. By the way, stochasticity is a main issue here that I think is important for determining the tracer populations that we will use in the future surveys. So this is an issue that is very important. I think it's machine learning is a pathway to studying that stochasticity. Finally, we need to extend this to MOCs, and we need to study how to go from galaxies back to halos, because that's an interesting way of testing cosmology also. That's it. Thank you very much, and I'll stop there.